In your high school, you may have encountered the notion of determinants. More specifically, you learned to compute the determinant of a 2 by 2 matrix, which involves multiplying the diagonal entries and taking the difference. For the geometric interpretation of determinants, you should watch these videos on YouTube. In this video, we will learn about definition of determinant. The prerequisite for this video is technically nothing. Before jumping into the main content, it is important to have a basic background in naive set theory. We will define what a set is, function between sets, and Cartesian product of sets. A set is a collection of objects. Here are some examples of sets. In all of these examples, the objects are numbers. Let A and B be two sets. A function from A to B associates each element, x, of A to a unique element, y, of B, which is denoted by f of x. The Cartesian product of sets A and B is set of all ordered pair, x, y, such that x is an element of A and y is an element of B. Here is an example of the Cartesian product of a set with the elements 1, 2, and 3, taken with itself. The elements of the Cartesian product lie in a two-dimensional plane, specifically on the vertices of a 3 by 3 grid. For sake of simplicity, we will work with real numbers, though it can be easily generalized to an arbitrary field or even a ring. An m by n matrix over real numbers is a function from vertices of an m by n grid to real numbers. We denote a matrix as a rectangular array with m rows and n columns. We use this notation to denote the set of all m by n matrices over real numbers R. Often, it is convenient to represent matrix A in terms of its rows. Let R and S be 1 by n row matrices. We give structure to these matrices by defining addition and scalar multiplication. The addition of two row matrices, R and S, is defined to be a 1 by n row matrix in which each entry is the sum of the corresponding entries of R and S. The multiplication of a row matrix R by a real number C, so-called scalar multiplication, results in a 1 by n row matrix where each entry of R is multiplied by C. Let n be a natural number and D be a function from set of all n by n matrices over R to real numbers. We say D is n-linear if D is linear in each row. That is, in each row, D preserves row addition and scalar multiplication. As an example, let's find two linear function in its generic form. Suppose E1 and E2 are the first and second rows of a 2 by 2 identity matrix. Let matrix A be a 2 by 2 matrix over real numbers. Express the first and second rows of matrix A in terms of the rows of the identity matrix. D is two linear function. Observe image of matrix A under D can be simplified using two linear condition. D is linear in first row, so it preserves row addition. And scalar multiplication. D is linear in second row. We can shrink the second row in a similar manner. We obtain the expression for the image of matrix A. That means D is entirely determined by where D maps these four matrices. Don't you agree D kind of looks like our good old determinant function on 2 by 2 matrices? To be precise, if D maps those four matrices to specific real numbers, then D is the determinant function that we are familiar with. This motivates our next definition. We say D is alternating if, given a matrix A with two identical adjacent rows, D maps matrix A to 0. Now we will prove an important result, which will be useful in later part of the video. Suppose D is an n-linear and alternating function. Show that if a prime is a matrix constructed by interchanging two rows of matrix A, then image of a prime is the negative of the image of matrix A. Let us first look at how D behaves when we swap two adjacent rows of A. Simplifying the image of this matrix will lead us to our desired result. Since D is n-linear, D preserves row addition in ith row and I plus 1th row. Since D is alternating, the image of a matrix that has two equal adjacent rows vanishes. The second and third terms are the image of A and the image of B, respectively. The image of matrix obtained by swapping two adjacent rows of A is negative of the image of matrix A. If we interchange two adjacent rows of matrix B, its image is exactly the image of matrix A. That means each time we interchange adjacent rows, its image changes sign. We will obtain a prime by interchanging adjacent rows of matrix A, certain number of times. Write rows of matrix A, interchange the ith row with the I plus 1th row. Then interchange row I with the row ahead of it. Continue interchanging rows in this manner until row I is in the jth position. It took us k interchanges to achieve this. Now interchange row J with the row behind it. After k minus 1 such interchanges, J is in the ith position. Thus, we have obtained a prime from A. The total number of adjacent row interchanges is 2k minus 1. Since 2k minus 1 is an odd number, the image of a prime is negative of the image of A. One point I would like to emphasize is that any other sequence of adjacent row interchanges to obtain a prime from A will always result in a total number of interchanges being odd. Now, let's revisit our previous example of a generic two-linear function on 2 by 2 matrices over real numbers. If we impose the additional condition of alternating on D, then based on the definition of alternating and the lemma we just proved, we have following. Substitute these values into the expression above. After simplification, the resulting expression represents the image of matrix A. If we assume the image of 2 by 2 identity matrix to be 1, then D is precisely the determinant function on 2 by 2 matrices that we know of. Now, we are ready to define determinant function. We say D is determinant function if D is n-linear, alternating, and maps n by n identity matrix to 1. And there you have it.